So this is part 4 of Advanced Engineering Mathematics, number 10. The practice final exam number 10. Let f equal yz, comma x squared, comma xyz. We're going to evaluate the closed line integral here, f dotted with dr, where c is the boundary of the plane x plus yz equals 1 in the first octant. We're going to use Stokes' theorem. So Stokes' theorem problem here, and our f that equals yz, comma x squared, comma xyz. So if we compute here del cross f, so the curl ijk for this determinant, and then partial with respect to x, partial with respect to y, partial with respect to z, yz, x squared, xyz for the setup. So performing the computation here, the curl, this del cross f that equals xz, comma y minus yz, comma 2x minus z. The plane was given as x plus y plus z equals 1, so isolating z, z equals 1 minus x minus y. And using upward orientation, this ds vector here, 1, 1, 1, dx, dy. I'm sorry, the set equal to 1, 1, 1, dx, dy. Then we could say the curl there, the del cross f dotted with that ds, that equals xz. When we perform the computation, that equals xz plus the quantity y minus xz plus the quantity 2x minus z. So from there, del cross f dotted with ds, that equals y plus 2x minus z. And from before, in terms z in terms of x and y, z equals 1 minus x minus y. So y plus 2z minus the quantity 1 minus x minus y, that equals 3x plus 2y minus 1. So setting this up, the projection is the triangle. Bounds x greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 1. So y is going to be less than or equal to 1 minus x. So here for this closed line integral, f dotted with dr, that's set up from 0 to 1, 0 to 1 minus x in double integral form, 3x plus 2y minus 1 dy dx. 0 to 1, 0 to 1 minus x, this will be 3x plus 2y minus 1 dy dx. That's going to come out to, when we perform the computation for this integration, 1/3. So for this closed line integral, this f dot dr, we get 1/3. Okay, so that was number 10. Moving along to number 11. So here in cylindrical coordinates, we want to evaluate this dot product here, del dotted with a, for a equals the quantity. So this is a divergence technically of a. For a equals r squared cosine theta r hat plus rz theta hat plus quantity z squared plus rz hat. And then verify the result in Cartesian coordinates. So this is a curvilinear coordinates problem. So we were given this for a, r squared cosine r hat plus rz theta hat plus quantity z squared plus rz hat. So in cylindrical coordinates, that del dotted with that a, that's going to equal 1 over r times this partial derivative with respect to r a sub r plus 1 over r partial derivative of a naught with respect to theta. I'm sorry, partial derivative here a sub theta with respect to theta plus the partial derivative of a sub z with respect to z. So here a sub r is r squared cosine theta, a sub theta is rz, a sub z is z squared plus r. So 1 over r partial with respect to r a sub r, that equals 1 over r partial with respect to r cubed cosine theta. So that equals 3 r cosine theta. Also 1 over r, the partial of a sub theta with respect to theta, that equals 0. And the partial of a sub z with respect to z, that equals 2z. So the dot product of del and a, that equals 3r cosine theta plus 2z. And since that r cosine theta equals x, this becomes del dot a, or a vector, equals 3x plus 2z. And this happens to agree with the Cartesian form. Okay, so that's number 11. And building on that, let's go to number 12. So for the scalar field for number 12, phi x, y, z equals ln x squared plus y squared plus z squared. Part A, compute the gradient. Part B, determine the Hessian matrix. Part C, find the Laplacian. And part D, determine all singularities. Okay, so this is a tensor gradient Hessian Laplacian problem. So phi x, y, z, that equals ln x squared plus y squared plus z squared is given. So we're going to let r squared equals x squared plus y squared plus z squared. Then phi is ln r squared. So the gradient is del phi, and that equals 1 over r squared del r squared. And that's going to equal 1 over r squared, parentheses, 2x, comma, 2y, comma, 2z, close parentheses. So del phi equals 2 over the quantity x squared plus y squared plus z squared, x, y, z. And the Hessian entries are going to be h sub ij. That equals this second partial phi, and then over the partial here, x sub I, x sub j, and then 2, my apologies for this delta here, delta sub ij over r squared minus 4 x sub I, x sub j over r to the 4th. So h is going to be 2 over r squared I minus 4 over r to the 4th times this matrix here. First row respectively, first row is x squared, x, y, x, z. Second row, x, y, y squared, y, z. Third row, x, z, y, z, z squared. So the Laplacian is the trace of the Hessian. So we have the Laplacian here. Phi equals 6 over r squared minus 4r over r to the 4th. So this del squared phi equals 2 over r squared. And the only singularity occurs where r squared equals 0. So the singularity is at 0, 0, 0. Okay, so I went over that rather quickly. My apologies if I mispronounced anything. So that's part 3. Thank you very much. And I'm sorry, that's part 4. Thank you very much and have a great day.